The ocean just had a really bad day. That's how one scientist summed up the 80-foot wall of water that smashed into the Draupner oil platform on New Year's Day, 1995. But here's where it gets controversial. What if that monster wasn't a freak accident at all? Just the ocean following its own rules a little too perfectly. The wave that rewrote physics textbooks at 3:20 p.m. on January 1st, 1995. The North Sea looked ordinary until a single 80-foot crest rose out of nowhere, buckled steel railings like tin foil, and hurled multi-ton equipment across the deck. For centuries, sailors had whispered about such walls of water, but scientists dismissed them as sea stories. Draupner changed everything. For the first time, laser sensors captured every millisecond of a rogue wave in the open ocean. The data was no longer folklore. It was forensic evidence. Francesco Fedele, an associate professor at Georgia Tech School of Civil and Environmental Engineering, calls that moment the day the ocean stopped bluffing. He explains, seafarers always insisted these waves appear suddenly and tower above the rest. Until Draupner, we thought they were exaggerating. Rethinking the rogue, myth versus math. The discovery ignited a scientific gold rush. Was the ocean breaking its own laws, or had we simply misread the fine print? Fedele, long skeptical of the reigning theory, assembled an international team to dig deeper. Their tool, 27,500 wave records gathered over 18 years in the North Sea, the most exhaustive oceanic dataset ever compiled. Each 30-minute record tracked height, frequency, and direction with the precision of a heartbeat monitor. The verdict? Rogue waves don't need exotic forces or cosmic coincidences. They only need two everyday ingredients to line up at the wrong moment.
The old theory, modulational instability. Picture a crowded highway where every car suddenly decides to occupy the same lane at once. That's modulational instability, a domino effect, where tiny timing errors cause energy to pile into one rogue lane, creating a single towering wave. Textbooks love this explanation because it worked beautifully in wave tanks and narrow channels where energy can only flow forward. But the open ocean is more like a city roundabout than a one-way street. Energy can scatter left, right, up, down, and diagonally. Fedele's team found zero evidence of modulational instability in the North Sea data. In plain English, the old theory collapses once you leave the laboratory. The new recipe, ordinary physics, extraordinary timing. Instead, two surprisingly simple mechanisms do the heavy lifting. One, linear focusing. Imagine several small ripples racing toward the same point from different angles. When their crests overlap perfectly, they stack like Lego bricks, forming one giant crest. No dark magic, just good or terrible timing. Second-order bound nonlinearities, a mouthful, but think of it as nature's Photoshop filter. This effect stretches the crest skyward while flattening the trough, adding an extra 15 to 20% height boost. It's the difference between a gentle hill and a sharp mountain peak. When these two mechanisms synchronize, the ocean doesn't break the rules, it exploits them. The wave grows, steepens, and suddenly becomes the stuff of nightmares. From academic curiosity to life or death forecasts, Fedele is blunt about the stakes. Every year, rogue waves injure crews, sink ships, and damage billion-dollar platforms. Calling them unpredictable is no longer acceptable. Current forecasting models still treat these giants as statistical ghosts, appearing at random. Fedele's research says otherwise. They're extreme, yes, but they're explainable. The ripple effect is already spreading. The National Oceanic and Atmospheric Administration, NOAA, and Chevron have folded Fedele's insights into their risk models. Instead of shrugging at the next bad day, engineers can now design decks, railings, and hulls to survive the precise forces these waves generate. Machine learning, teaching computers to read the ocean's mood. Fedele's next frontier is artificial intelligence. By feeding decades of wave data into machine learning algorithms, his team trains software to spot the subtle fingerprints that precede a rogue wave, specific combinations of height,
direction, and timing that human eyes miss. The goal: forecasts that warn captains hours, not minutes, before a monster arrives. The takeaway: nature's surprises aren't supernatural. Rogue waves aren't cosmic pranks. They're the ocean's way of reminding us that rare doesn't mean impossible.
Given enough time, even ordinary waves can align into something extraordinary. As Fedeli puts it, rogue waves are simply the ocean having a bad day. They speak the same language as every other wave. We're just learning how to listen. Controversy Corner. Are we underestimating the danger? Some researchers argue that climate change could make these bad days more frequent by altering wind patterns and storm intensity. Others insist the statistics haven't shifted. Our instruments have just gotten better. Who's right? Could tomorrow's seas be measurably riskier? Or are we finally seeing what was always there? Your turn. Do you believe rogue waves will become more common as the planet warms? Or are we just better at detecting them? Drop your thoughts below. Agree, disagree, or share a sea story of your own. The floor is yours.